Hello everyone, my name is Tianyu, and while I'm super bummed that I won't get to meet any of you in Montreal this weekend, I still hope that this recording of my talk will be of use to you. So, without further ado, let's get started. So, as you probably already know, the title of my talk is called The Zen of Git. And you might be wondering, what on earth is she going to talk about, right? Like, what do the words Zen and Git have to do with each other? And I felt much the same way when I first started using Git many, many years ago. I was really scared to do anything beyond the most basic commands, and I didn't really know much better. But it is my hope that in this talk I can make you feel much more ease at Git and with using it, and maybe even enjoy using it. Who knows? It was really funny. I discovered this blog post called the Zen of Git when I was doing a bit of research for this talk, and I had no idea this existed beforehand. But this is actually a parody on the Zen of Python. And the Zen of Python, for those of you who don't know, is just a set of idioms for how to program in, or how to think about programming in the Python programming language. And the person who wrote the Zen of Git decided to take that and make a little bit of fun at it to poke fun at Git. And so you have stuff like ugly is better than beautiful, complex is better than simple, readability is meaningless, errors should never be comprehensible, there should be no obvious way to do it, although there may be endless non-obvious ways to do it. So if you've used Git at all for any amount of time, you can probably relate to at least one of these statements. And so for sure, so can I. And I thought this was pretty funny, but also if we're making so many jokes about it, maybe there's also something that we can do in order to help people be less, feel less this way about Git and more confident with it. So how do we go about doing this? I would say that we need to start at the beginning. So where is that? Where is this? This is a picture of the city of Königsberg in the 1800s. And at this time, there was an open mathematical problem which asked whether or not it was possible to cross each of the 7 bridges exactly once. And it turned out that a mathematician by the name of Euler solved this problem. And the way that he did it was really interesting, and I want to talk a little bit about that now. So instead of looking at this map and thinking, oh gosh, it's really complicated, how do I go about solving it? This is what he did. First, he drew 7 lines that corresponded to the 7 bridges. Then he drew essentially blobs that were connected by these 7 bridges, because that's what you really care about. You really care about the fact that you have these bridges and which bridges connect to which land masses, right? So if you take the map away now, you end up with something that looks like this. And if you use a little bit of imagination, I can redraw the red blobs to be something more uniform and make them into circles. And why am I showing you this? So it turns out that this structure is actually called a graph. It has a name. It's called a graph. And the official definition of a graph is something that contains a set of nodes, which are circles, and edges, which are the lines that join these circles. And there's actually a whole field of mathematics that is dedicated to this, called graph theory. But graphs, circles, edges, lines sounds a little bit abstract, right? And it doesn't sound like something that you can actually really think about in the real world. But it actually turns out that graphs are really, really useful for modeling things in the real world. Let's look at one example. So let's say you're using a social network. I'm sure most, if not all of you, have had some experience with this. You can think of yourself as a node, right? You're a node, you're an entity in the network. Now, there are also other entities. There are other people in the network. And you can think about, like, for the most part, you don't know those people. You're not related to those people. But as soon as you add them as friends, you suddenly form a link between the two of you, right? Like on Facebook, if I add you as a friend, then you're going to be my friend, and there's actually a relationship between us. We know each other. Well, you'd hope, right? So in that case, you would depict this in a graph by using another node to indicate the friend, and then a line to indicate the fact that you and the friend have a relationship. And so in this case, you can see that I have 3 friends, right? And it's not much of a stretch to think that each of these 3 friends can also have their own friends. And so I'm sure you're familiar with the concept of friends of friends, and like friends of friends and friends. And you can think of this as like you go on and on and on, and there isn't really an end to this. Another thing that is really useful is instead of just having a line connecting nodes, you can actually have arrows that connect these nodes. And this models a different kind of relationship. So whereas in the first case, these relationships are essentially two-sided. You and I have both agreed that we are going to be friends. So there is no like I am your friend and you are my friend. But in another kind of social network, for example, if we go with the example of social networks, you can think of something like Twitter, where you can follow someone, but they don't necessarily need to follow you back. So inherently, the relationships there are one-sided instead of two-sided. So in this situation, it's actually really useful to model this using an arrow as an edge instead of just a straight line. And so you see here, if we make this example more concrete, you have you, and you are following one other person because you are pointing, your node is pointing to their node, and that person you're following has 4 other people following them. So they're quite popular, right, in this very small network. And you yourself are also reasonably popular in the sense that you have 2 followers. Now, I can also follow one of my followers back, and in that case, I would then add the arrow back. Now, this kind of structure with the arrows has a special name. So it's also a graph, but it is called a directed graph because the edges have directions, because they have an arrow, and that arrow indicates a particular direction. Now, why am I talking to you about directed graphs? What does this have to do with Git? We're in a Git talk, right? So directed graphs are important to at least know a little bit about because they are actually the core of how Git stores your project's history and files. So Git, actually, underneath the hood, is a directed graph. So given that as a starting point, how does Git actually do anything with the graph? What does that actually look like? So we can take a look now. Let's say that you have an empty Git repository, so you have nothing, and you want to add these files here for the first time, let's just say. Now, what would you do? You would git add and then git commit, right? And after you make your commit, these files would be added. But what actually happens when you do the git commit? Let's see. So the first thing that Git does is it looks at all of the files in your in the commit that you want to create. So in this case, we have 3 files, and let's go through them one by one. So the first file is index.js, and you see index.js is a JavaScript file. It contains some code, right? So what Git does is it takes the contents of your file, and then it appends at the front, or it prepends a header that starts with the word blob, followed by the content length of the blob, followed by a null byte. And then it takes the header and the contents of your file and then stores this as the contents of a file on disk. And the file name of this file is not index.js, but it is the SHA-1 hash of the contents of this file. So this kind of object, so here it's called a blob because a blob is a specific type of Git object that corresponds to files. So Git will do the same thing for all the other files. So in this case, 2 more. So we end up with 3 blobs. But you notice that these blobs, while they do have the contents of the original file, they actually don't have anything about the file name, right? Like in our index.js, we have no idea that this blob f2b7de even corresponds to index.js. So how does that work? Well, this is where the third kind of object comes, the second kind of object comes in, and that is a tree object. So a tree object is used to indicate the structure of your files and folders, but also it is used to map file names to SHA-1 hashes of blobs and trees. So you see in this case, JS is a folder, so therefore it has to have a tree object that corresponds to it. And inside JS, we see that there is one file, index.js. Now, index.js here is actually represented by the blob f2b7de. So therefore, we have one line in our tree file that indicates this. And again, just like blobs, trees also have a prepended header as well that indicates it's a tree. A similar thing happens for the source folder, except that the source folder is a little bit more interesting in the sense that it contains a file and a folder. Now, the file will appear as one line similarly to how it did before. It says it's a blob, the blob has a particular hash, and this hash corresponds to this file name. But now it also contains a folder, and we know that a folder is represented in Git by a tree. And so this entry here will indicate that it is a tree, and the tree has this hash, and this tree has the name JS, which is the name that we know of. And finally, the same thing will happen also at the top level. So you can see how with these two types of files, we've actually built a complete picture of our file structure at this particular point in time. And now all we need to do is to have a commit that is the entry point for this file structure. So a commit is a third type of Git object. And like the other ones, it has its own header that starts with the word commit to indicate that it's a commit. And then it also contains a line that references the top level tree, so that it knows what is the top level entry point to the file structure at that particular point in time. And the rest of the commit file or the commit object will just contain the metadata that you are used to seeing in your Git commits. So the author, the timestamp, the commit message, and so on. And so even though Git implements blobs, trees, and commits as files on disk that essentially have pointers to each other within the contents of the file, conceptually, you can think about it as having these circles and edges here as a graph. So Git has implemented this as exactly a direct graph, which goes back to why I introduced it in the first section. Now, what happens if I make a change? So let's say I decide to change one of the files that already exist and add a new file. So in this case, Git is going to create two new blobs for the new file and the changed file. Now, this is all Git is going to do, because Git is going to see that the other files haven't changed, and so even if it tried to create a new file, it wouldn't need to, because the SHA-1 hash would still stay the same, so you can simply reuse what's already there. Now, because these two files are in the top level of the Git repository, the top level tree object needs to change, because remember, the entries inside the tree indicate the hash and the file name. So now we know the hash has changed because the contents have changed, and so therefore we need to recreate the tree object at the top. And finally, again, we need a new commit, because the commit is really the entry point to the snapshot of the files at that time. As for the rest of the trees and blobs, since they haven't changed, Git is actually going to just reuse them. Another thing that's important to note is that a commit is always going to point to the commit before it, and not the other way around. So this is what it would look like. Just to make sure that we really understand what's going on, let's look at one more example. So let's say that I decide to change the index.html. Now, of course, again, because the contents of index have changed, we need to create a new blob for it. But this time, because index is within the source folder, we know that source is going to have a listing for index, right? And because that index listing has changed due to the hash having changed, we need to recreate the tree corresponding to the source folder. And again, we also need to recreate the top level tree because one of the items inside it, namely the source folder, has changed. Finally, again, we create the commit. And all other references are simply reused. So you can see here that this is really important. This shows us something really important, which is that Git stores commits as entire snapshots of the repository. It does not store them as diffs, which is what you may think it does, and which is what I totally thought it did as well. But no, it stores complete snapshots at every single commit. And you might think, well, shouldn't this make it really big and blown up? But we know that this is not the case because you can see here, Git only stores, or it only creates a copy of what has changed. If something hasn't changed, it just reuses what's already there. So this is how Git represents objects in history as a directed graph. Now that we've seen this, let's see how we can add some extra data on top of the graph in order to make even more sense of it and in order to help us understand some Git commands later. So now we'll look at some metadata, and I'll explain why we call them references in a moment. So let's say that we have these 3 commits here, and we know that newer commits will always point to older commits. And we also know now that each of these commits has their own top-level tree, and each of those top-level trees have some number of subtrees and blobs, and then some of them may be reusing objects from previous commits. This is all cool, we've just seen this. Now, I can, independently of what's already been stored here, I can add some metadata or labels on top of what is already there in order to help me kind of understand what's going on. So one kind of label that I think is really useful is called a branch. And a branch is a type of reference, which is a type of label. And the special thing about a branch is that it's essentially a flag, or you can think of it as like a post-it note that I'm holding on to, but as soon as I make a change, I move that post-it note to the newest commit or the newest change that I've made. So in this case, let's say I'm on the testing branch, or I'm working on the testing branch. Then if I make another change, then my testing branch essentially moves to that new change that I made. And again, when I make another change. How are these actually implemented? So they may seem really complicated or mysterious, but they're actually extremely simple. So if you ever like have the interest for this, to actually look at this, if you were to look at what a branch is, you will find that it is simply one file that has one line, and that line is the commit hash of the latest commit of that branch. And the name of that file will be the name of the branch. So in this case, we have checkpoint as a branch. Now, the name of this file will be called checkpoint on the file system, and the contents of this file will be C3AF blah, 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 which is the hash. And that's all a branch is. When you make a commit on that branch, Git is just going to update the SHA-1 hash inside that file. It's very, very quick and very, very lightweight. Another kind of reference, and it's not really a kind of reference because it's quite special, in the sense that there is only one of it in your repository, and that is called head with capitals. And the purpose of head is to keep track of where you are in the graph. Because if you imagine, if you have many branches, you have many commits, it won't be too hard to get lost, right? And so head kind of is like a way of Git trying to figure out or like keep track of where you are in the whole thing. Now, why is head useful? So head is useful to indicate, of course, if you're on this branch or on another branch. And head is really just another file that has a file name capital HEAD, and its contents contain the thing that it's it is at the moment. So in this situation where I am on the testing branch, the contents of the head file is simply going to be testing. If I were to move to another branch, say checkpoint, then the contents of my head will simply contain the word checkpoint, and that indicates that I'm on the checkpoint branch. And similarly, I don't have to be on a branch, I can be on any commit that I like. And in that case, if it's on a commit, then the contents of head will just have the commit hash. Now, head is particularly useful when I'm in this situation. Let's say I go back, rewind a few commits, and I'm back to the beginning, right? If I now have two branches on one commit, how do I know which one I'm working on, right? Because there are two branches, and I can work on them separately, and they're two distinct things, even though they happen to be on the same place at the same time. So head is really useful in this situation because head will be pointing to one of the two branches, and whichever one it's pointing to will be the one that I'm working on. So in this case, I'm on checkpoint. In this case, I'm on testing. Another type of reference that is useful to know is a tag. And a tag is very similar to a branch, except for the fact that it does not move as you make more commits. So if I'm, say, here working on the checkpoint branch, if I made a commit at this point, then the checkpoint branch would also move with my new commit. But when I have a tag like this tag named special here, that tag is not going to move. That tag stays at that commit until I decide to remove it or do something else with it. So in a way, you can really think of a tag as a nickname for a commit, because otherwise the commit will be referenced purely by the SHA-1 hash. But if you give it a tag name, it's a little bit easier or more human-friendly way of referring to a specific commit. Similarly, you also have remote branches. So these are branches that have they've come from a Git server, and oftentimes they are branches that other people are working on. And these can also be represented using this exact same way that we're representing local branches as well. So now that we've seen how Git stores all of the data and history as a graph, and how we can also add metadata on top of this graph, let's actually talk about how we can understand common Git commands and make more sense of them using this. So let's go with this example here. We have some commits right here. And we also have some branches here. So right now we have 3 branches. We have a master branch, and that is the common ancestor of feature and test branches. And because my head is pointing at test, that means that I'm on the test branch. Right, so what will happen if I do git merge feature and I'm on the test branch? So what Git does when it does a git merge is that it creates a merge commit. And once it creates that merge commit is special because it doesn't have any changes, but it does contain 2 parents. You can see it's pointing to 2 commits. One, which is my branch, and another one, which is the branch that I'm trying to merge. And this is actually all git merge does. It just creates that merge commit that joins the 2 branches together. And then, because it's a branch, then we also update the branch pointer. So that's actually all git merge is. Nothing more and nothing less. What happens if we do a rebase? So you hear a lot about, like, should I use rebase? Should I use merge? What's the difference? Let's look at rebase here. So what rebase is going to do in this case is it's going to see that there are 2 commits on my branch that are not on the feature branch. Then it's going to take each of those and apply them one by one, like so. And it's important to note here that the 2 commits that were originally on my branch are not going to be copied exactly. So the contents will be copied exactly, but the hashes will be completely different. So I'm actually duplicating those 2 commits and putting them onto the feature branch. So that's important to note here. Once it does that, then all there's left to do is to update the branch pointer. So you can see the difference here between merging and rebasing is that merging is going to create a merge commit, but it leaves all the existing commit alone. Whereas on the other hand, rebasing is going to create new commits and update the structure of my branch in a way such that merge does not do. So that is actually a major difference between the two. And depending on your situation, you need to be a little bit careful. Now, if I were to run git gc, which I don't need to do manually, but I want to talk about here out of interest. If I want to do this, then Git is going to see that those two commits that were on my branch previously are now no longer on any branch at all. So git gc will actually delete them. Another common command that you might use is git revert. And git revert is a really interesting one because depending on what you're trying to do, it may not do what you want. So this is why it's important to understand what exactly it's doing. Let's say I want to revert the commit on the left. And in that commit, I introduced just one line, hello world. Well, git revert is going to take the changes that I made in that commit, which is only one line in this case, and then it's going to create a new commit that contains the opposite of what I did. So in this case, because I added a hello world in the original, it's going to subtract a hello world in this commit, like so. And then update the branch pointer. So you can see here that even though the net effect of the adding and the deletion, and adding and the deleting is that the line is not there anymore, but you can still see that the original commit is present, and so is the commit to delete it. So if you had committed something sensitive in the first commit and you needed to get rid of it, then git revert is not going to be what you want, because someone can still go back to the commit that you were trying to revert. What does checkout do? So checkout is really interesting because it can be confusing for some people, but the way I like to explain it is that it's actually really straightforward. The role of checkout is to update the contents of your head pointer. So here I'm pointing to test. So my head will simply contain the word test. If I now say git checkout master, the contents of head is just going to be master. And because Git uses head to know where you are, Git is now going to see head is pointing to master, master is pointing to D23AC, D23AC, DD23AC contains a tree, and then it's going to create the file structure at that particular point in time. I haven't changed anything else, I've simply just gone back in time. Now, if I were to check out to a specific commit, it's slightly different. So you might think head is going to point to the branch at that commit. But no, because I specified that I wanted to check out to a specific commit, head is going to contain a reference to that commit. And this is okay, there's nothing wrong with that. This is just me going back to that point in time. But you're going to see a maybe scary warning about something called a detached head. And you might think, okay, this is like, well, what's going on here? This is really scary. But all this means is that if you are at this commit and you decide to create another commit, then if you now moved away from this commit to another commit, it's really easy for you to lose that work. And that's it. That's all Git is saying. Git is just trying to make sure that you don't lose your work in this case. Okay, so we looked at checkout. So what about reset? Git reset is really interesting. So in checkout, we saw that we are changing just the contents of head. Nothing else changed. So the branches still stay the same, and so on. The commits still stay the same, everything remains, the structure remains as it is. With reset, it's slightly different. So reset changes the branch pointer instead of the head pointer. And what do I mean by that? So if I am on the test branch, and now I do git reset feature, then the test branch pointer is now going to point to the same commit as the feature branch pointer. But head, in this case, is still pointing to test. So now you see, I've essentially used reset to modify the commits on my branch, right? And this is completely different to checking out, which was just moving around. A quick look at reset in more depth. So you can have the standard situation where you're totally happy with, you have all three trees in sync. And then you can do a soft reset. And a soft reset is simply just a undo of the commit, but everything is still staged. You can also do a mixed reset, and this is a default, so you don't need to specify this argument. And a mixed reset is interesting because this is the same as undoing the commit and undoing the staging. So this is as if you hadn't committed anything, you hadn't added anything. And finally, you have reset hard. Reset hard you should use with caution because reset hard will set the branch pointer to wherever you specify, no matter where it is, and it will discard all of the changes between the point you're moving to and the point you're moving from. So unless you know what you're doing, take a little bit more care with this command. Now, so we've looked at how Git stores objects. We saw that we have a series of commits that are linked to each other, and each of these commits point to a tree, which could point to any number of trees and files. And we also saw that we can also add some metadata on top of this structure to allow us to use Git more effectively. And finally, we saw that a lot of common commands, which may be unclear for people, can actually be explained quite simply in terms of all of this structure here. And so with all of this, I've given you essentially the Zen of Git. And with this knowledge, I hope that you will be able to use Git more effectively, more confidently, and even maybe enjoy it. Thank you very much. And feel free to contact me on Twitter or LinkedIn if you have any questions about this talk. And again, please stay safe.